All right, so Oceanography, Section 2, Ocean Currents. Ultimately, what we're really getting into is the movement of the surface water. We will talk a little bit about deep ocean currents, but the majority of what we talk about today will pertain to surface ocean currents and the movement of those currents. So our objectives are describing how wind patterns and the rotation of Earth along with continental barriers affect surface currents in the ocean. We'll talk about major factors that determine the direction in which a surface current circulates. Hint, hint, wink, wink, nudge, nudge. Maybe it was these things that were up here in the first one. And we'll talk about how differences in the density of ocean currents can affect deep currents. So it's important to recognize our surface currents are mostly directed by winds and Coriolis and the continents and their arrangement, whereas our deep ocean currents are really developed based on differences in salinity. All right, so what is an ocean current? In geology, a current is a horizontal movement of water in a well-defined pattern, such as a river or a stream. Oceanographers identify ocean currents by studying the physical and chemical characteristics of the ocean water. We place ocean currents into two major categories: surface currents and deep currents. The factors that affect surface currents include the horizontal movement of our wind belts on our planet. So the wind belts that are moving around our planet also guide ocean currents, because some of the energy from those wind belts is transferred into the water itself, thereby moving it in specific directions. Earth's rotation is another thing that causes our currents to move. And Earth's rotation leads to us having these things called gyres, which are kind of like those small eddies you saw in the simulation, where we get this rotation that happens and this cycling that happens from the cold water in the polar regions. That water then makes its way kind of along some continents down to the equator, where it's rewarmed. It then heats up. It makes its way back northward to the polar regions, and it loses its energy in that process. So now we've got cold water, and that process starts all over again. So not only do we have wind currents that are driving this, but we also have Earth's rotation, and then the continents obviously do not allow for currents to move through land masses, so the continents in their shape actually drive some of our currents as well. So our wind has kinetic energy, and that energy is transferred from air to the ocean, and the water at the ocean surface then begins to move. So we've talked a lot about global wind belts from prior units. The trade winds were those wind belts that came from Europe over to the Americas. The westerlies are the wind belt that we live in. The wind comes out of the west and moves towards the east. And so these currents of air, as they are moving or making their way around the globe, they're going to move the ocean water as well, causing surface currents. In both hemispheres, we have trade wind belts that are pushing currents westward across the tropical latitudes. And then our westerlies are going to push ocean currents eastward along the higher latitudes of the northern and southern hemispheres. Our continents lead to a barrier. As those continents are sitting in place and currents are moving, the water that comes in contact with the continent itself gets deflected one way or another. So continents can influence surface currents also. Typically, they end up deflected one way or another as those currents come towards a continent, towards a landmass. The Coriolis Effect, recall, is due to the spinning of Earth. And just as a little bit of review, the Coriolis Effect is the apparent curving of a path of a moving object from an otherwise straight path due to the rotation of Earth. We talked about that during our weather unit. Wind belts and ocean currents follow a curved or circular pattern that is caused by this rotation of our planet. This causes gyres. Gyres are huge circles of moving ocean water found above and below the equator. If we're talking about specific oceans, each ocean has a couple of gyres. Like, for example, north of the equator, along our eastern seaboard in the Atlantic Ocean, we have the North Atlantic gyre, where ocean currents make their way northward along our eastern coast, make their way all the way over towards Europe, move back down towards the equator again, and then come back on the trade wind belts back towards the Americas. In the northern hemisphere, our gyres flow clockwise or to the right. In the southern hemisphere, they flow to the left or counterclockwise. We have a number of major surface currents, and we're going to go through quite a few of them here. Warm equatorial currents that are located in the Atlantic, Pacific, and Indian Oceans, they occur right near the equator. And each of these oceans has two warm water equatorial currents that move in a westward direction. One of them is north of the equator, the other one is south of the equator. These are westward flowing currents. Between them lies a much weaker current that flows eastward called the equatorial countercurrent. And the equatorial countercurrent flows right along the equator. Currents in the southern hemisphere. In the most southerly regions of oceans, we have westward winds that produce the world's largest current, which is called the Antarctic Circumpolar Current, also known as the west wind drift. Every year, there is a boat race that is a circumnavigation boat race that goes all the way around the Earth. And a lot of these racers enter the west wind drift because it has no interruption. There's no continent in the way. And so they can make their way all the way around the entire southern portion of our planet in the ocean without having a continent where they run into it or a deflection of any ocean current. And so the wind is just continuous there. And it goes through all three of our oceans. So what's the world's largest ocean current? The one that runs all the way around the globe, no interruptions? That's the west wind drift, or the Antarctic Circumpolar Current. And we're going to see a picture of this here in just a bit. Currents in the North Atlantic. So I talked a little bit earlier about how we have warmed water from the equatorial regions that moves northward along our eastern coast. That current is called the Gulf Stream. The Gulf Stream is very fast moving. It's fairly deep as far as it being a surface current, and it moves warm Atlantic water northward. Once we get up to Greenland, the Gulf Stream widens, and then it eventually becomes the North Atlantic Current. And it still is transporting heated water. It's still moving water that is warm. The North Atlantic Current is then going to push this warmed water all the way over to England, or even up towards Norway. And so now we've got this warm water from the Gulf Stream that's getting pushed over to other parts of Europe. Once it gets near Europe, it splits, and the current that goes northward up towards Norway is called the Norway Current. So it's bringing warm water northward to Norway, and so that helps to keep Norway's coast relatively ice-free because there's a bunch of warm water that's moving that way. The other part of the split goes southward, and that's the Canary Current. And the Canary Current sinks south back towards the equator along the western coast of Europe. In the middle of these currents, we have this large empty area of pretty relatively calm water, that is called the Sargasso Sea. The Sargasso Sea is actually full of all kinds of debris that's floating on the surface of the water just because the motion of those currents around it causes all of the materials that have been collected to kind of end up in the middle of the ocean. We have similar patterns to this in the northern Pacific. We have the warm Coriolis current that runs up along Japan. So it's moving heated water from the equator northward along Japan. So it's the Pacific equivalent of the Gulf Stream. It flows northward along the east coast of Asia. And then it flows towards North America as the North Pacific Drift. And so now you've got this warmed water that's heading towards the east over towards like Alaska and northern California or Washington State and Oregon. It eventually flows southward along California as the California Current, and so now it's lost all of its energy, and it's moving colder water from Alaska downward. So the California Current is a cool current. So here's a diagram showing what we've just been talking about. We've got the North Equatorial Current that's taking heated water. You'll notice it's colored in red, indicating that this is warm water. It then changes into the Gulf Stream. The Gulf Stream runs northward along our eastern seaboard until it hits the North Atlantic Current. Some of the water from the Labrador Current is pushed southward. Some of the cooler water from the East Greenland Current is pushed southward. And so there's mixing that takes place, and so we get a lot of eddy formation right in this area. Where the North Atlantic Current splits, it makes its way up towards Norway as the Norway Current, still moving warm water. Or the water that is cooled then moves southward in the Canary Current back to the North Equatorial Current to be rewarmed. And so we get this process, this large gyre of moving water. The same thing over here in the northern Pacific. We have a current in the northern hemisphere that's still moving to the right. It's moving clockwise. We have the North Equatorial Current still, then hits the Coriolis Current, makes its way up along Japan. It then turns into the North Pacific Current. It does split when we get over towards the western seaboard, the northwest, the Pacific Northwest. It moves against Coriolis and spins counterclockwise as the Alaska Current because the landmass itself directs the movement of that water. So the Alaska Current actually defies Coriolis and it goes in reverse direction. Or that water sinks down in the California Current back towards the equator to be rewarmed. Notice that these currents in the northern hemisphere, all except for the Alaska Current that's being guided by our landmass, all of them are spinning clockwise. In the southern hemisphere, these currents are not spinning clockwise, they're spinning counterclockwise. And this is due to Coriolis. Same thing over here in the South Atlantic. The Brazil Current is then hitting the Antarctic Circumpolar Current. It is, that water's cooled. It then makes its way up and along Africa to the South Equatorial Current, and that process happens over and over and over again. The Indian Ocean has its own current as well. The South Pacific Ocean has its own current as well. Deep currents are movement of water as well. And this forms because of salinity differences in water. As we get very cold, dense water, it likes to sink. And so it sinks beneath the warm surface water. And the movement of polar waters is usually a result of differences in that density because of the salinity differences. Remember, density is a result of salinity and temperature differences. Remember that if we're colder water, we end up with a higher density. If we have more salt dissolved in that water, again, we have a higher density. We call this the Antarctic bottom water. So the temperature of the water near Antarctica, it's really cold. That's supposed to say -2 degrees Celsius. So we're below freezing. And the reason that it can get that cold is because of the salt content. So the water salinity is extremely high, allowing that water to get below freezing. And so it makes it the densest and coldest water on our planet. This is the Antarctic bottom water. And that dense cold water sinks into the bottom of the Antarctic. It then moves through the ocean basin, and it will not recirculate to the surface for hundreds or even thousands of years. So why is the Antarctic bottom water the densest and the coldest in the world? Well, it's because it's really cold and because it's high in salinity. We also have a North Atlantic deep water current. So in the North Atlantic, south of Greenland, the water is very cold. It has high salinity as well. And this cold, salty water forms a deep current that moves underneath the Gulf Stream. We also have a current that flows out of the Mediterranean Sea. Remember when we looked in our previous section, we saw the Mediterranean Sea had a really high salt content. It was really saline. Well, that causes water to become more dense. And if water is more dense, as it's flowing out of the Mediterranean Sea into the Atlantic, it's going to sink down into the Atlantic Ocean and create a current that is a deep ocean current as well. We can also get turbidity currents. Think of a turbidity current like the last time you went to the lake and you started walking out in clear water on the lake, and as you're stepping in the bottom of the lake itself, you're kind of kicking up mud or dirt, right? What that does is it creates water that ends up a higher density because you've got a bunch of materials that are either becoming more dissolved or it's just mixing with the water itself that's surrounding it, so you get a higher density. So that water ends up with this kind of muddy look to it, and with a long enough period of time, it'll cause that water to sink down. If you're kind of just walking out across the bottom, a lot of times you'll notice when you take a step, it kicks up a plume of mud or material from the bottom. It kind of spreads out and moves up, but then it sinks right back down. That is a turbidity current. So turbidity currents can happen anywhere in the ocean, especially along the continental margins. And it can create a difference in density that leads to flowing of water also.